Hello everyone! Today we are going to be discussing blackbody radiation and its significance to quantum mechanics. My name is Becker and let's get started with this topic. So first of all, what is a blackbody? You can think of the heat you may feel radiating from the embers of a campfire. This is a simple example of a blackbody, but other examples include our solar system's star, the sun, as well as glowing pieces of heated metal. Now, for an ideal blackbody, it is going to be a red-hot piece of metal with a spherical cavity inside. We can kind of see that in this figure right here. This cavity can be observed through a small hole that does not interrupt the conditions taking place inside of here. Now, when at a uniform temperature, the blackbody will emit a specific frequency distribution of light that solely depends on its temperature. Lower temperatures will have a smaller frequency of lights, that being red and orange in the visible spectrum, whereas higher temperatures will have a higher frequency, that being green and blue and even purple in the spectrum. Now this makes sense given our experience with everyday life. The hottest part of a campfire is going to be yellow in the middle, while the coolest part is going to be the red trickles of flames at the top. Now with many natural phenomenon, we can model what this actually looks like. So this graph right here is going to be experimental data showing how increasing temperature will increase both the peak frequency of emitted light and the amount of energy overall. We can see that right here, it's plotted spectral density versus frequency, and we just have these curves corresponding to different temperatures of our blackbody. And as you can see, these lines do not actually overlap, and there's a clear trend in the increasing peak frequency of our lights as we go higher in temperature. We can kind of see that going through right here if we imagine a line plotted through there. Now, to actually model these curves, we can first look at what classical electromagnetic theory predicts. So first of all, we are going to have our equation, which is going to be the spectral density as a function of frequency and temperature, which is going to equal 8 pi times the frequency squared over the speed of light to the cube times the average energy of the oscillating dipole of our solid. So just like that. Now spectral density is going to define the amount of energy emitted by the blackbody at a particular frequency per unit area and unit frequency. We can kind of see that right here, but resultingly the spectral density is going to have units of energy over volume times frequency. It is going to be something like joules over meters squared times our frequency, so hertz, just like that. Now, speed of light is pretty straightforward. That's just going to be our 2.998 times 10 to the 8th meters per second. But this average energy of our oscillating dipole is a bit more confusing, something we don't come across too often. That is going to be the oscillating dipole in our blackbody solid, which results from the positive and negative charges in our atoms oscillating to emit energy at the frequency they oscillate. Now, taking this information, we can actually add a little d nu factor right here and here, and this will allow us to determine the energy density observed within the interval d nu at the frequency nu. Okay, so classical theory predicts that the average energy of a simple oscillator is related to temperature by the E oscillator average, just like that, equals the KB times T. Now this KBT is going to be our Boltzmann constant and is going to have a value of 1.381 times 10 to the negative 23 joules per Kelvin. Now we can plug this equation into our spectral density equation to get the spectral density as a function of frequency and temperature equals the 8 pi times the Boltzmann constant times T times frequency squared over our C cubed. And that is what our classical theory predicts. So what happens if we actually model this? So plotting this equation at 6,000 Kelvin is going to give us a line that looks like this. Here is what our experimental data says. It shows that we have an increasing line, have a peak right here, and then it slopes back down again. But as you can see, our classical predicted model is a little bit different. We have similar behavior down at lower frequencies of light, but as we get higher, the classical equation continues to increase as the frequency increases. This line is actually going to go up to infinity, and considering how the area under the curve of our line gives the total energy per unit volume of the field of our black body, this suggests our black body emits infinite energy at any temperature above absolute zero. Considering how this breaks multiple fundamental laws of the universe, it is clear that classical mechanics is the wrong way to approach blackbody radiation. Now, so far in our discussions, we have shown that quantum mechanics has different properties than classical mechanics. I mean, an example of this would be a soccer ball trying to roll over a hill. We know that based on the kinetic energy, whether it will or will not roll over this hill. But if we have an electron and give it a certain amount of energy, we don't know if it can actually cross some sort of quantum level bump. It will in some cases, not in others, but we cannot accurately predict this. So far, we've shown many cases where classical mechanics just falls short in predicting how things behave on the quantum level, and that is where we need to dive more into quantum mechanics. And this is the case with blackbody radiation. As shown by this graph, the divergence between our classical mechanics and our experimental data at high temperatures and high frequency radiation shows that something is going on here that we are not accounting for. Now, the physicist Max Planck was able to model this difference by assuming the radiated energy was related to frequency, given by the equation E equals n times h over nu. Times nu. H is going to be Planck's constant, which is found to have a value of 6.626 times 10 to the negative 34 meters squared times kilograms over seconds. Quite a value. We also have this n value, which is going to be just a positive integer, which can be 1, 2, 3, and so on. So therefore, given at any set frequency, the energy emitted by a system is going to be quantized. It can only have certain values. Now, this is a very important discovery that shows that energy in quantum theory can only take on this discrete set of values for each frequency compared to the continuous values predicted by classical mechanics. Great, so using this information, Planck was able to obtain a new value for our energy of the oscillator, which we can write as the average energy of our oscillator equals h nu over e to the h nu divided by the Boltzmann constant times temperature minus 1. And we can just do that. And there we go. We can then plug this equation into our spectral density formula to obtain this right here. We did a little bit of simplification, but if we go ahead and plot this equation, we get lines that much better match our experimental data. We can see that our curve is going to go up, and once we hit our peak frequency, it's going to curve back down again, just like this. And considering our classical prediction, this sort of new modeling using quantum mechanics shows that energy is quantized for blackbody radiation. So that is our discussion of blackbody radiation. To summarize, a blackbody is a solid that emits a characteristic frequency of light based on its temperature. Now, classical theory is not enough to accurately represent blackbody behavior because it predicts a blackbody above absolute zero will emit infinite energy, which is just not possible. Now we can accurately model blackbody radiation by assuming energy emitted can only take on a set of discrete values for each frequency, given by our equation E equals nh times nu. Anyways, thank you all so much for watching, and have a great day.